Hello viewers, welcome to another interesting lecture of digital communication. In this segment, we are going to discuss non-coherent type of the modulation. But before discussing today's lecture, let us have a recap. This lecture is totally conducted by Ganon, powered by Wishbag. I am your mentor, Professor Aditya De. So, let us discuss digital modulation technique division. There are two types of the digital modulation technique. One is coherent, another is non-coherent. In coherent type of the modulation, it is also three types. One is binary, another is M-array, another is hybrid. In case of the binary, you already aware of there are two states of the level, and there may be ASK, FSK or PSK. In M-array coherent modulation, it may be M-array ASK, it may be M-array FSK, or it may be M-array PSK, or maybe QPSK. In case of the hybrid coherent modulation, it is M-array APK or M-array QAM. Now let us discuss non-coherent type of the digital modulation technique. It may be binary or may be M-array. In case of the binary, it is ASK, FSK or DPSK. In case of the M-array, it may be M-array ASK and M-array FSK and M-array DPSK. Now let us discuss the ASK type of the non-coherent modulation. The transmitter is same as coherent type of the ASK modulator. The difference is only in the receiver. In coherent detection as used in analog communication does not require carrier for reconstruction, or non-coherent detection does not require carrier for reconstruction. The received signal is passed through a band pass filter, or in short it is known as BPF. The simplest form of incoherent detector is the envelope detector as shown in this figure. The output of envelope detector is the baseband signal. The baseband signal is recovered, its samples are taken at regular intervals and compared with a threshold. If ZT, that means output, is greater than the threshold lambda, a decision will be made in favor of symbol 1. If ZT, the symbol value is less than the threshold, what happened? It will be made in favor of symbol 0. Now let us discuss frequency shift keying. Figure shows the block diagram of non-coherent or incoherent type of the FSK demodulator. Transmitter is same as coherent type of the modulator. The detector consists of two bandpass filters, one tuned to each of the two frequencies used to communicate zeros and ones. The output of the filter is envelope detected, and then baseband detected using an integrator and dump operation. The detector is simply evaluating which of the two possible sinusoids is stronger at the receiver. If we take the difference of the output of the two envelope detector, the result is bipolar baseband. The resulting envelope detector output are sampled at small t equal to k capital TB, and their values are compared with the threshold, and the decision will be made in favor of symbol 1 or 0. Now let us discuss comparison of digital modulation schemes. Complexity of transmitting equipment for PSK, FSK and ASK are very little different. At receiver, coherent schemes are more complex among non-coherent. DPSK is more complex. If bandwidth is most important, then VSB is the best. If power requirement is important, then coherent PSK or DPSK is most important. If equipment complexity is limiting, then non-coherent schemes are important. Now let us discuss one numerical. Binary data has to be transmitted over a telephone link that has a usable bandwidth of 3000 Hz and a maximum achievable signal to noise ratio of 6 dB at its output. Number A, determine the maximum signal rate and probability of error if a coherent ASK scheme is used for transmitting binary data through this channel. And number B question is, if the data is maintained at 300 bits per second, calculate the error probability. Now, let us solve it. If we assume that an ASK signal requires a bandwidth of 3 RB/Hz, then the maximum signaling rate permissible is given by bandwidth is equal to 3 RB is equal to 3000. Therefore, RB equal to 1000 bits per second, and average signal power is a square by 4. Noise power is 2 into eta by 2 into 3000. Then average signal power by noise power is equal to 4, which is a square by 12,000 eta. Then a square by eta is 48,000. Hence, a square by 4 eta RB is equal to 12 and PE is equal to Q function of root 12. You are already familiar with Q function, which is Q 3.464, which is nearly equivalent to 0.0003. Now for the solution part B, if the bit rate is reduced to 300 bits per second, a square by 4 eta RB is equal to 40. Then PE is equal to Q root over 40, which is Q 6.326, which is equivalent to 10 to the power minus 10. Let us discuss another numerical. Binary data is transmitted over an RF band channel with a usable bandwidth of 10 MHz at a rate of 4.8 into 10 to the power 6 bits per second using an ASK signaling method. The carrier amplitude at the receiver antenna is 1 millivolt and the noise power spectral density at the receiver input is 10 to the power minus 15 watt per hertz. Find the error probability of a coherent and non-coherent receiver. Let us discuss the solution. Bit error probability for the coherent demodulator is PE is equal to Q root over A square capital TB by 4 eta. Here A is 1 millivolt, TB is equal to 10 to the power minus 6 by 48, eta by 2 is equal to 10 to the power minus 15 watt per hertz. PE is equal to Q root over 26, which is equivalent to 2 into 10 to the power minus 7. For non-coherent ASK, PE is equal to half of exponential minus A square capital TB by 16 eta. Therefore, PE is equal to 0.0008. So, what we have discussed in this lecture? We have discussed non-coherent ASK, then we discussed non-coherent FSK, and lastly we solved some numerical problem. That's all for this segment. Practice the numericals repeatedly. Stay tuned to Ganon. Stay safe, stay healthy. Bye.